I think this is question number 4. So if you look at this square loop, the area of the loop is given to us, resistance is given to us, magnetic field is uniform in space. We need to find the work done by the external agent in pulling out the loop. So in order to find the work done by the external agent, we need to imagine that initially the whole of the loop is inside the magnetic field. Suppose loop is in the position A. So when you are just taking out the loop from A and suppose you go into this new position B, clearly if there is no friction force, then because the loop is being pulled out slowly, so it means it does not accelerate. So from A to B, we don't need to apply a force, we just need to move the loop slowly. So we don't want to apply any external force. So it is only when the loop is going outside the magnetic field. So now here if you see, if you just name this loop as A, B, C, D, so a section of length x of AB, this lies inside the magnetic field. So electromagnetic induction takes place, and now a force will act on the loop ABCD. So see how a force acts. First let us see in what way the induced current flows, because the magnetic field goes into the plane of the page. So in order to, because the flux is decreasing in magnitude, if we take area vector of this loop going in the same direction as the magnetic field, which is inverse, same direction as the direction of the external magnetic field B. So what happens is an induced current flows in the loop in this sense, so that magnetic field in the same direction, that is going into the plane of the page, is produced. Now if a induced current flows like this, BC is already outside the magnetic field, so no force acts due to the magnetic field on BC. But on AD, if the length of AD is called as L, and if an induced current I flows, then this much force acts due to the magnetic field on the part AB. If you consider a small section of AB, let's say over here, then on this small section AB you can see, since the current is flowing toward this side and magnetic field goes in, so if you apply IL vector cross B vector, the force on AB acts like this on a small section of AB. And if you consider a small section of CD in which current flows in the opposite direction to AB, and again magnetic field going inward, so IL cross B points in this. So now these two forces, they just cancel out, being equal in magnitude and opposite in direction. So the net force on AB and the net force on CD, they just cancel out. On BC, no force acts. So the force on the loop ABCD is simply the force acting on, magnetic force acting on the arm AD of the loop, right? So that is the force acting on the arm AD of the loop. Now it has been given that the loop is pulled out slowly, so which means that the length BA comes out of the loop in 0.1 seconds. So that basically gives you the velocity of the point B. And since there is no acceleration, so B moves with a uniform velocity. And if you consider the length x of the loop lying inside the magnetic field, then the flux associated in this position, which is shown in this diagram, is L, the length of AD, into x into magnetic field, and the rate of change of flux will be given by, because L and B are constant, dx by dt is simply v, velocity of the point P. So this velocity is basically L upon 0.1, which is 10 times L. So you just take this as 10 times L square into B over here, and B is given A square, L square stands for the area of the loop. So magnetic field is 0.40, right? So magnetic field is 0.40. So 4 into 10 to the power minus 1, and this 10 they are totalized. L square is 2.5 into 10 to the power minus 3. So this gives us 10 into 10 to the power minus 3. So this gives us 10 to the power minus 1. Now one small point over here is, like, because there are 100 loops, so we expect the flux to be multiplied by n, which is the total number of terms in this square loop. So this is n is 100 and we need n here. So a factor of 100 gets multiplied over here like this. So this is 10 to the power minus 2 and 100, this gives you 1. So this is basically the induced EMF. It is 1 volt, and the current flowing in the loop is then current flowing can simply be found by dividing this induced EMF by 100. So the induced EMF, if you can see, this 2.5 into 10 to the power minus 3 is the area of the loop, 100 is the number of turns, this is 0.4. So when this is 0.4, you basically 0.4 into 2.5 should give you 1. So this basically gives us 10 to the power minus 3 into 100, which is 0.1 volts. So zero point 0.1 divided by 100 ohms will give you 10 to the power minus 3 amperes as the current flowing in the loop. So once we have the current flowing in the loop, we are able to find magnetic force on AD, which is current I, L. The length of this loop is simply the square root of 2.5 into 10 to the power minus 3, which is 5 into 10 to the power minus 2, which is 5 into 10 to the power minus 2. I into L into B. Magnetic field is 0.4. So this gives us 5 into 0.4 is simply 2 into 10 to the power minus 5 volts. So this basically gives you the magnetic force. Now again, since there are 100 turns, so we expect that the force is also to be multiplied by a factor of 100 over here, because there are 100 parts, 100 lengths like AD. So when you have this multiplied with 100, this gives you in newtons the force is 2 into 10 to the power minus 3 Newton. So that is the force acting on AD, and that is the external force required to compensate or balance this force. So if you multiply this with the length of AB, then you get the work done. Work done is the external force multiplied by the length, and this is 2 into 10 to the power minus 3 newtons into length is so many meters, 5 into 10 to the power minus 2 meters. So this gives you 10 into 10 to the power minus 5, which is 10 to the power minus 4 joules. So that is the work done, 10 to the power minus 4 joules. This part should be the answer. So another of the question which was asked from me is this question. You can check which question is this. So basically, it is a very easy question because there are two parts to this loop. We have the iron part and we have the wooden part. So you can check. Initially, the whole of the iron part, it lies in the uniform magnetic field. So a flux is associated with this uniform magnetic field over this area, and if pi r square by 2 is the area of this semicircle, which is shown here, multiplied with the uniform magnetic field, then this is the initial flux. And finally, when this loop takes a turn and this iron part, it comes like this, then you have a situation where this is the wooden part, the green part is the wooden part. So now the whole of the iron part, it is outside the magnetic field. You see this, the iron part is out of the magnetic field, only outside the magnetic field. So when you just find the flux, finally the flux will be obviously 0, because there is no magnetic field associated with the iron part anymore. So average EMF is simply the change in flux upon the time interval over which that change occurs. So change in flux, so we can find in magnitude. The magnitude will be simply this. So this will be pi r square b upon 2 from here, and divide by the time during which this change is taking place. So it's given to us that it takes 2 seconds for this to happen. So now pi is 3.14, radius is 10 to the power minus 1 in meters, and you have to square it. So 10 to the power minus 2, 1 upon 4. So we get this as the value of the magnetic field induced EMF. So this should be the induced EMF produced in the loop. And the value of the magnetic field also needs to be substituted here. This is 2 into 10 to the power minus 4. So you have 2 over here, and 10 to the power minus 6, 1.57 into 10 to the power minus 6 volts. So that should be the answer to this. So now let's look at this question. The question which was asked as a doubt. Now, if you can see this, the conducting wire is AOB, and it is given that it is being moved along this direction with a certain velocity along its perpendicular bisector, the angle AOB. So this velocity is along this direction, right? So when you talk about this, so basically this velocity has two components, and one of the components lies in this direction, perpendicular to AO, and the other component lies along AO only. Now since this angle is theta by 2, the angle over here is corresponding angle theta by 2. So this velocity has two components, one which is perpendicular to the length of the rod, which happens to be v sine theta by 2. Now if you consider or imagine an electron over here, now this electron has two components of its velocity, one over here and the other in this direction. Now just forget this for the time being. This component of the velocity of the electron, it does not lead to any induced EMF or significant induced EMF in the conductor AO. Now that is because ये वाली जो velocity है ये इस direction में, और इस velocity के साथ perpendicular इसी plane में अगर हम एक line ऐसे draw कर दें, इस तरीके से ये वाली red line के along, this line is perpendicular to this velocity because जो force लगेगी इस electron पर V cross V magnetic field की वजह से Q times V cross V, that force has to be perpendicular to both magnetic field and velocity. So that force has to be along this black line. And if you take that force, so the width of this conductor AO, this width is very less. So if you talk about the motional EMF, तो motional EMF जब आएगी तो motional EMF क्योंकि इलेक्ट्रॉन्स क्या है एक फेस पर इकट्ठे हो जाएंगे, तो अगर V क्रॉस B आप निकाल रहे हो तो V ऐसे और B इनवर्स है, तो V क्रॉस B में यहाँ पे इलेक्ट्रॉन्स आएंगे और यहाँ पर इलेक्ट्रॉन्स की डेफिशिएंसी होगी अगर हम AO को ऐसे इमेजिन करते हैं AO को, पर ये विड्थ बहुत कम है, तो we don't expect any significant voltage because of this component of the velocity. So V parallel, इसको अगर हम V parallel बोलते हैं, this does not lead to an induced EMF, but V perpendicular, अब इलेक्ट्रॉन को अगर हम ऐसे मानते हैं, ऐसे मूव कर रहे हैं, अब इसके साथ परपेंडिकुलर और मैग्नेटिक फील्ड के साथ परपेंडिकुलर ये वाली लाइन आती है, तो अब V क्रॉस B किस तरफ आएगा, V क्रॉस B हैज टू बी, अगर हम राइट हैंड रूल यूज करें और B से लेकर B तक फिंगर्स को घुमाएं तो मैग्नेटिक फील्ड गोज इन, सो V क्रॉस B हैज टू बी along from O to A. V क्रॉस B की डायरेक्शन कितनी आ जाएगी, क्योंकि V ऐसे है और B इनवर्स, V अगर हम अंदर की तरफ बनाएंगे तो ये आपको 3 डायमेंशन में इमेजिन करना होगा, तो V क्रॉस B is towards OA vector, okay, OA vector. So minus E times V cross B will be towards which direction? This will be towards, it will be in the direction of AO vector. तो O के ऊपर इलेक्ट्रॉन्स एक्यूमुलेट होंगे और A पर इलेक्ट्रॉन्स की डेफिशिएंसी होगी, तो यहाँ पर इलेक्ट्रॉन्स एक्यूमुलेट होंगे, तो आप ये कह सकते हो कि A पॉइंट पर हायर पोटेंशियल डेवलप हो जाएगा रिलेटिव टू द पॉइंट O. So voltage between O and A points will therefore be, हमें ये V perpendicular, अगर हम डायरेक्ट मोशन EMF का फॉर्मूला यूज करें where let L be the length of AO, तो V perpendicular आ जाएगा V sin theta by 2 into B into the length of AO, and you can see the length AO is small l, not capital L, we can take it as small l. Now we can talk similarly about the BO part. Now if you talk about BO part, now you can similarly argue, आपको बस वही आर्ग्यू करना है इसमें भी, कि जो आपका BO पार्ट है उसकी वेलोसिटी इस डायरेक्शन में, इस वेलोसिटी के दो कंपोनेंट्स हैं, एक ऐसे और एक ऐसे, जो पैरेलल कंपोनेंट है टू द लेंथ, दिस डज नॉट लीड टू एनी मोशन EMF, perpendicular component leads to motion EMF. Now this angle is theta by 2, so V perpendicular is V sin theta by 2, V perpendicular is V sin theta by 2, and V perpendicular L will be the motion EMF, so that will be again V sin theta by 2 upon into L. So it is the same magnitude as this, but now let us see which point is at a higher potential, O or B. तो अगर हम V perpendicular cross B लेंगे तो magnetic field goes into the plane, तो अगर आप magnetic field V cross B निकालते हो, इस V का क्रॉस प्रोडक्ट लेना है B के साथ, तो अगर आप V क्रॉस B निकालते हो तो आप देखो B से लेकर B तक फिंगर्स को कर्ल करेंगे तो BO वेक्टर की डायरेक्शन में एक वेक्टर, अगर हम V परपेंडिकुलर क्रॉस B निकालते हैं तो दिस विल गिव अस अ वेक्टर इन द डायरेक्शन ऑफ, आपको बस मैग्नेटिक फील्ड को इमेजिन करना है गोइंग इनटू द प्लेन। तो V परपेंडिकुलर ऐसे, मैग्नेटिक फील्ड अंदर की तरफ। तो इट इज अ लिटिल बिट लाइक दिस, जैसे ये अगर XY प्लेन है तो मैग्नेटिक फील्ड तो है नेगेटिव Z एक्सिस की डायरेक्शन में, ठीक है, Z एक्सिस ये, मैग्नेटिक फील्ड तो है नेगेटिव Z एक्सिस, और V परपेंडिकुलर इज इन द XY प्लेन। तो आप इमेजिन कर सकते हो कि P क्रॉस B किस तरफ आ जाए, ठीक है। तो अगर नहीं भी आ रहा तो इसको आप सिंपली इमेजिन करो, मेक टेक अ पेंसिल and place it in front of your eyes, or take your pen and place it in front of your eyes. You consider V perpendicular from one of the ends of the pencil and B vector going perpendicular to this. And when you calculate B cross B, तो B cross B निकालेंगे तो it will be along BO. And minus E times B cross B will be in the direction of OB vector. तो B के ऊपर इलेक्ट्रॉन्स इकट्ठे हो जाएंगे और O के ऊपर हायर पोटेंशियल आएगा। तो अगर ये सपोज 5 वोल्ट्स पर है और ये सपोज 0 वोल्ट्स पर है, तो B के ऊपर 0 से भी ज़्यादा पोटेंशियल लोअर है, तो यहाँ -5 वोल्ट्स है। तो बेसिकली यहाँ मैग्नीट्यूड था 5 और यहाँ से यहाँ ड्रॉप हो रहा है और यहाँ से यहाँ ड्रॉप हो रहा है। तो यहाँ से यहाँ जो टोटल ड्रॉप आ जाएगा दैट विल बी ट्वाइस ऑफ दिस PVL sin θ/2। दैट शुड बी द आंसर।